Welcome. In this session in linear data analysis, we'll explore how a hyperplane separates centroids of data that have been clustered using the k-means algorithm and the ordinary Euclidean norm. We'll represent our clusters by centroids, so it'll be vector g1 and vector g2, and we'll represent our hyperplane, double-barreled H, by using a normal vector w that's not necessarily of unit length, and a bias scalar b. Let's begin by reminding ourselves of the geometry of this situation. What we have is a centroid. Let's suppose that this is centroid G2, and we have centroid G1. And we know that the hyperplane has to be orthogonal to this difference vector, which has to be w. And that hyperplane also has to have some reference point r that is on the hyperplane. And from this, we can readily deduce these values, w and b. So immediately, we can say that w is directed from our second cluster to our first cluster. And this is a choice that we're making. We're saying that G1, the centroid of cluster 1, represents some positive, not in a value sense, but just some positive set, and the G2 represents some negative set. Now, we can also find R is the midpoint of G1 and G2. That is, this separating hyperplane is going to be in the middle. And that implies that we can write W as, we can say that is simply G1 minus G2, and we can write our reference point as G1 plus G2 over 2. Now, how can we find the equation, that is, how can we find this value b? Well, let's do this. Let's consider some vector v that is exactly in this hyperplane. We know that v has to satisfy this equation. We know that if we take the dot product of w and the difference between v and r, that has to equal 0. Well, that's equivalent. Let's distribute this dot product over the vector, in this case, difference, but it's really an addition. So that is w dot v minus w dot r has to equal 0. And that has to be equivalent to w dot v plus b equals 0. And that implies that b has to equal, so that implies that b is minus w dot r. And if we want to, we can expand that out fully in terms of G1 and G2. And we can say that that is minus, so W was G1 minus G2, and then R is G1 plus G2 over 2. And so we can find W directly and we can find B directly. Now, how can we use this? Well, now let's consider we'll put this in quotes, a new vector u. And what we want to say is u in set 1 or set 2. And that, if we were just given centroids, we would have to do this. We would have to take the vector difference and take the squared norm, take the vector difference, take the squared norm, and we could certainly do it. But it's a much faster computation if we use the hyperplane. So we'll say that U is in set 1 if and only if it's on the positive side of the hyperplane, and we can represent that. Now I'll use transpose instead of a dot product because this is a more usual way to find this, is W transpose U plus B is greater than or equal to 0. Does it matter that W is not a unit vector? Well, no, it doesn't. If it really mattered, we could have defined W as G1 minus G2 over the norm of G1 minus G2. But for the purposes of doing these computations, it's faster to simply find W and find B once, and then afterwards it's an inner product and add a scalar and then compare that to 0 to determine whether to classify U as being in set 1 or set 2. Let's take a look at how this works on some data. Let's recall Fisher's iris dataset, and particularly recall the sepals. So the sepals are the covering part of the flower, and in Fisher's iris data, these are the data vectors where one component is the sepal length in centimeters and the other is the sepal width in centimeters. And this cluster represents the beachhead type iris, which is Iris setosa, and this larger cluster represents two other species that we have combined. And the question is, what happens when we run k-means clustering? Well, when we do, what we find is this. Here I've assigned colors to the clusters, so this is cluster 1 and this is cluster 2. And you can see that there is a vector in cluster 1 that seems anomalous. That is, a human might say, well, I want to include that in this cluster, but k-means has decided that it is in this cluster. And the reason is that this capital X represents the centroid of this cluster, and this capital X, which is a little harder to see, represents the centroid of this cluster. And this vector is simply closer to this centroid than it is that centroid. That's a computation we can do. We can also calculate the hyperplane and illustrate the hyperplane. And what we can see is that the hyperplane decision is this line, and consequently this vector is on the positive side of the hyperplane and gets classified into cluster 1, and all of these are on the negative side of the hyperplane and get classified into cluster 2. This anomalous situation is one where we've used a machine learning method, k-means clustering, and it's made some decisions, and those decisions are not necessarily ones that a human would support.